Hi, this video explains two regularization techniques that are very important for the training of neural networks: dropout and batch normalization. So our learning goals are to use dropout and batch normalization during the training process as regularization techniques, and to understand the behavior of batch normalization and dropout during training and inference with model.train and model.eval. So as we have discussed before, overfitting is when the model performs too well on the training data, but poorly on the validation data. Underfitting happens when the model struggles with both training and validation data. Regularization helps us strike the right balance, improving the validation performance. Regularization is in general a term that we use for every technique that we use to combat overfitting. So dropout is this technique to combat overfitting that reduces the connections that we have in a neural network at random. So it's just turning the activations into zero. Like we're gonna select a random fraction of the activations that we have in a particular layer, and then we're going to turn them to zero. This prevents the neurons to be too reliant on specific values on a given neuron, and improves the generalization by forcing the network to learn more robust representations. The dropout rate is typically set between 0.2 and 0.5. That means between 20% of the connections and 50% of the connections are disappearing at random. So let's see the effect that this would have on an image. Here we see that we apply dropout after doing convolutions and a ReLU activation. We do a single convolution on a grayscale image, and then we do a ReLU nonlinear activation that is going to turn the negative values into zero. Then we're going to apply dropout, and this would randomly set 50% of the activations to zero. This only happens during training. This regularization reduces overfitting by ensuring the network does not rely too heavily on specific activations. We see the code to implement this common pattern in PyTorch, and this is the most common order in which we see the operations. First convolution, then the nonlinear activation, then dropout. It's important to understand that every time that we present this image to the model, the dropout is going to happen differently. So different pixels are going to be set to zero at random. The model is never going to see the same image twice. So we see that this is another data augmentation technique, very similar to what we saw in the previous video, with the difference that this data augmentation technique is not happening on the original input images, but on the images that we're processing with the convolutions and the nonlinear activations. This slide explains batch normalization. In the code, the convolutional layer extracts features from the input, followed by the batch normalization with 16 feature maps. This is what is highlighted here. You see that the number of out channels 16 matches the number of num features, which is also 16. So the batch normalization operation works very similarly to the input normalization operation that we saw on previous videos. The difference is that this is going to be operating on the activations that we have on a particular batch. So if we have a batch that contains 32 images, then the activations of these 32 images while we're training are the ones that are going to be considered when we do the computation of the mean and the standard deviation. So besides transforming the activations by using the mean and the standard deviation of the batch, we're also going to do scale and shifting transformations. And this is something very similar to what we saw on the previous video. This is something that will allow the network to do some data augmentation while it's training. It's a very interesting effect, and here we see it. Here we see an original image after it has been convolved, and this is a map of activations. So we see here that these activations are going to be in a range that maybe has some negative values, some positive values. By doing the scaling, that is the standard scaling that comes from the mean of the activation and the standard deviation of the activations, we're going to put the data in a different location, but then we're also going to be moving this data with affine transformations, just like we did before on the input image. And I recommend that you go back and double check the similarities between what we're doing here and the random affine transformation that we did in the previous video. The main difference is that we don't apply the affine transform to the input image, but to the activations that we produce during training. And it's useful to visualize the effect of batch normalization. This slide shows how this would be in a very reduced dataset that has only 2 dimensions. We have only x and y values. So on the left, the red points represent unnormalized data, which can have varying scales and ranges, and the blue points are normalized data, rescaled to have a mean of 0 and unit variance. We already saw in the video about input normalization how this speeds up training. It's also something that is gonna help us when we do it to the activations, because the gradients that we're gonna produce are now something that are gonna be on a more restricted range, and this means that training is gonna be more numerically stable. On the right of the plot, we see green points showing normalized and scale data, where the scale is adjusted by the learnable parameter gamma, that here is set to 2. And this is something that we would learn during training. So we will set this learnable parameter to values that actually reduce the loss function. As we saw on the previous slide, this scaling serves a data augmentation process. This process ensures stable activations with respect to the gradients of the loss and helps the model learn efficiently at the same time. So we're doing 2 things at the same time. We're making the model be more numerically stable, and we're also augmenting the activation data during training. And here we see another demonstration about what happens when we do the normalize and scale data. This is the shift part, where the purple points show the normalize and shift data using the learnable parameters beta x and beta y. This demonstrates how batch normalization not only standardizes, but also gives us this little bit of data augmentation. On the right, the red points are unnormalized data, and the purple points are fully transformed data that has been normalized, scaled, and shifted, so the full batch normalization transform. So this highlights the full effect of the batch normalization operation. In this slide, we're comparing the dropout behavior during training and evaluation. When we have model.train, which is the default behavior of the model, dropout is active and random activations are set to 0 after reloop, as shown in the noisy output that we see on the right. This regularization helps prevent overfitting during training. If we do model.eval, dropout is disabled and all activations are retained, ensuring that we have deterministic outputs for inference. And this distinction is very important for us to have consistent evaluation of the performance of the model. Here we also see how important this is during inference. What happens when we set up model.train and we run this image twice? We see that we have different probabilities for each time that we run inference. The output is non-deterministic. So for consistent and reliable inference, we need to switch to model.eval, where the dropout is completely disabled and we produce some stable predictions. And this demonstrates why proper mode switching is important when evaluating a model. Then we have the effect of doing eval model.eval on batch normalization. So the learnable parameters, which are called gamma and beta and are exposed as weight and bias in PyTorch, do not change or get turned off when we call model.eval. They remain exactly as trained and continue to scale gamma and shift beta, the normalized activation. So these are still going to be active when we do model.eval. Like the scaling and the shifting is still happening. The main difference when we do eval is that the running mean and the running variance, the track statistics for the whole training set, are used for normalization instead of the per batch statistics that are used during training. So in eval mode, we are going to be using the whole statistics of the mean and the standard deviation that we saw during the training of the model. And the scale and shift are still happening. This is very important to understand. Here we see the effect of batch normalization on predictions in a pre-trained ResNet 18 model, a model that has a lot of batch normalization. In model.eval, batch normalization uses global statistics, resulting in consistent and stable predictions that are actually quite good. If we do model.train, then batch normalization is going to rely on the current batch statistics, which is only one image, which can lead to unpredictable outputs. Like in this case, the batch size is only 1. And when we use a batch size of 1, we're going to introduce a lot of noise in the behavior of batch normalization. So this behavior emphasizes the importance of using model.eval during inference to avoid variability caused by calculations that are dependent on the batch. So this effect is most noticeable when we use very small batch sizes. And it's important for us to understand and remember that model.train is a default behavior of all PyTorch models. So this is present even if we don't call it. So we're going to get bad predictions out of our ResNet if we don't set it to model.eval because of the effect of batch normalization when we run it on small sample sizes. And it is important to discuss something that we see in forums and in the literature. It is sometimes said, although it is not a rule, that dropout and batch normalization can work against each other when placed together in a network. This is because the batch statistics can get noisy. When we do batch normalization, we rely on accurate estimates of the current batch mean and variance, and dropout randomly zeroes out the activations, changing the distribution within the batch and making those statistics more volatile, especially when we have smaller batch sizes as we saw. So it might be that they have a bit of conflict, like dropout tries to counteract the overfitting by randomly removing features, and batch normalization also tries to maintain like some stable feature distribution across training. But it also adds a bit of noise by the variance that we have in the different means and standard deviations that we compute in different batches. So this random masking that we do in dropout may interfere with the effort of batch normalization to keep the activations scaled and shifted in some consistent ways. And there is some redundancy here, so maybe it's not a good idea to use them together in many models, but there are no guarantees. It is important for us to do our own experiments and check the settings that give us the best performance in the validation set for our particular problem. Like the settings make a really big difference here. It might be like some particular combination of values of dropout and batch normalization give a better performance when used together than not using them together. It's very problem specific. So to wrap up this video, we saw that both dropout and batch normalization function as data augmentation that work on activations instead of input images. We also saw that dropout and batch normalization need to be controlled during inference. Model.eval is going to disable dropout completely, which is going to produce a deterministic output. However, batch normalization is still applied after model.eval. However, the difference is that when we do model.eval, batch normalization is going to use the mean and the standard deviation of the whole training set instead of just the batch. We also saw that batch normalization and dropout may act against each other. So both provide regularization effect, and combining them might require some careful tuning of their settings. That's something that you will need to explore on your own, and you're going to see this on the practical section of this particular lecture.